Okay, so we're gonna go through the temperature and heat notes. It's gonna be 2 pages worth of notes. We'll start with temperature. Temperature is the average kinetic energy of particles in a substance. So temperature has to do with how fast the particles, those atoms or molecules, are moving around inside of a substance. With our measurement and things this year, we've already talked about some different temperatures, but the US uses a standard Fahrenheit temperature scale. So some common temperatures that you should know in these different scales are water's freezing temperature, which in the US is 32 degrees Fahrenheit. Room temperature in Fahrenheit is about 70 degrees. Your body temperature should be 98.6 degrees Fahrenheit. And boiling water is 212 degrees Fahrenheit. Now, most commonly used scale is going to be what they use over most of the world, and that's going to be our Celsius temperature scale. This is used in most other countries. The freezing point of water in degrees Celsius is 0 degrees Celsius. Room temperature, or a comfortable room temperature, is about 25 degrees Celsius. Body temperature should be about 37 degrees Celsius. And the boiling point of water is 100 degrees Celsius. Now you should get used to using the Celsius scale, and you should recognize what is hot or cold in degrees Celsius. So this is a little poem that can help you remember some different temperatures in Celsius. 30 is hot, 20 is nice, 10 is cool, 0 is ice. Now the third temperature scale in your notes, we did talk a little bit when we talked about SI units, is our scientist scale, the Kelvin temperature scale. Water freezes at 273 degrees Kelvin. A comfortable room temperature is 298 degrees Kelvin. Body temperature is about 310 degrees Kelvin. And water boils at 373 degrees Kelvin. Now, if you notice, our Kelvin scale has much bigger numbers than either of the other two scales, and that has to do with the idea of absolute zero. Absolute zero is the temperature at which all particle motion stops. And this is only theoretical. We've never actually gotten all the way down to absolute zero in a lab, but it would be cold enough to where all of the particles, the atoms and the molecules within a substance, actually stopped moving, stopped vibrating, stopped shaking, stopped moving around. And that would be that 0 degrees Kelvin. And that's where the Kelvin temperature scale comes from. And so if that is our 0 degrees, freezing, even freezing water, would be all the way up to 273 degrees. Now, since we have 3 different temperature scales, you should know that you can convert between the different temperatures. We could take a temperature in Celsius and turn it into something in Fahrenheit, or vice versa. We have some examples down here at the bottom of your paper and all of the different conversion factors. Going from Celsius to Fahrenheit or Fahrenheit to Celsius is more difficult, but there are a couple of examples to show you how it's done. To find a temperature in degrees Celsius, starting with a degree Fahrenheit, you would subtract 32, multiply by 5, and divide by 9. As you can see in this example, 97 minus 32 is 65. 65 times 5 would be 325, and 325 divided by 9 would give us 36.1. So 97 degrees Fahrenheit would convert to 36.1 degrees Celsius. And we can do this the other way around. We could start with the temperature in degrees Celsius and solve for one in Fahrenheit. So if we started with 23 degrees Celsius, to get to Fahrenheit, we would multiply by 9, divide by 5, and add 32. So 23 degrees Celsius times 9 would give us 207. Divided by 5 would give us 41.4. And then adding 32 would give us 73.4 degrees Fahrenheit. Converting from Kelvin to Celsius or Celsius to Kelvin is much easier. In fact, Kelvin and Celsius use the same temperature scale gradient, meaning each degree is the same size. So raising up 3 degrees Celsius is the same as raising up 3 degrees Kelvin. The only difference is the starting point. So the starting point for degrees Celsius is 0 degrees Celsius, which is our freezing point of water. The starting point for Kelvin is our absolute zero. So it's way, way, way colder than freezing for water. That once we have our starting points equal, each degree is the same size for Kelvin and Celsius. To convert from Celsius to Kelvin, you would just add 273. And to convert from Kelvin to Celsius, you just subtract 273. All right, on to our next page. We're done with temperature and we're moving on to heat. So heat is the energy of particles. Heat is always moving from hot to cold. Heat does not move from cold to hot. Heat is the energy of movement, so it's always going from hot to cold. So for example, a cup of coffee will cool down because the heat energy inside of the coffee is moving into the surrounding air. So anytime we're talking about heat, we use arrows to show the direction that the heat is flowing. And in this case, our heat is flowing from our hot coffee into our cool air. So the arrows are going towards the cold. Now you try. Draw in arrows that show which way the heat moves when an ice cube is placed in a warm room. So the warm room and the cold ice cube. And remember, heat always goes from hot to cold, never the other way around. All right, so thermal equilibrium is our next definition. And thermal equilibrium is when all the temperatures are equal. And that happens when the heat energy stops moving, and that's when thermal equilibrium is reached. And so in our example above, if our hot coffee, if all the heat leaves our hot coffee and goes into the cool air, it will stop, the heat will stop moving once the coffee and the air are the same temperature. All right, so thermal energy is our heat energy. And thermal energy is the amount of heat energy in a substance. And that depends on the temperature of the substance. And it also depends on the amount or the size of the substance. And so an example we have here is Shaquille O'Neal. He's a really big guy, so he has a lot of thermal energy. He has a high temperature, he's exercising, and he also has a lot of mass, so he has a high thermal energy. If we were to compare his thermal energy to someone, say, like Justin Bieber, all right, the two things we would compare would be temperature, which we know humans have a body temperature of 98.6 degrees Fahrenheit or 37 degrees Celsius, and also size to determine thermal energy. So here's a picture to compare the two in size. So Shaq would have a much larger thermal energy than Justin Bieber because he has the same temperature but is a much larger size. All right, so one more for you guys to try. There's 3 pictures on your notes, a cup of water, an ocean, and a swimming pool. And it says to rank the following pictures of water from the most thermal energy to the least thermal energy if they were all at room temperature. So if they're all the same temperature, which one would have the most thermal energy, the least thermal energy, and medium thermal energy?